Category O, Lecture 16, Various Categorification Results. Let us recall our setup. We work with a semi-simple, finite-dimensional complexly algebra G with a fixed triangular decomposition into the negative part, the Cartan subalgebra, and the positive part. W denotes the Weil group of G, and associated with this triangular decomposition, we have the BGG category O, and it has as a direct summand its principal block denoted O0. We know that simple objects in O0 are indexed by elements in the Weil group in such a way that the notation LW stands for the simple highest weight module with the highest weight W dot 0. So here dot is the dot action of W on H star. We have other structural modules in this block. We denote by PW the indecomposable projective cover of LW, by IW the indecomposable injective envelope of LW, by delta W the Verma module with highest weight W dot 0, and by nabla W the dual Verma module with highest weight W dot 0. Finally, we denote by TW the indecomposable tilting module with highest weight W dot 0. We know that the category O0 carries the natural action of the monoidal category of projective functors. Let's recall what projective functors are. A projective functor on category O is a functor which is isomorphic to a direct summand of the functor of tensoring with a finite dimensional G module. So we have the classification of indecomposable projective functors on O0 due to Bernstein and Gelfand, which asserts that indecomposable projective endofunctors of O0 are in bijection with indecomposable projective objects in O0, and therefore are also in bijection with elements in W. For W in W, there is a unique indecomposable projective endofunctor denoted theta W of O0, which maps the dominant Verma module delta E, which is also the dominant projective PE, to the indecomposable projective module PW. So we denote by P00 the monoidal category of projective endofunctors of O0. Recall also that the center of O0, which is defined as the endomorphism algebra of the identity functor, the later functor is a projective functor. This is a projective functor theta E. So the center of O0 is isomorphic to the coinvariant algebra C of the Weil group W. There is a theorem which is due to Bachelin, which asserts that for two elements x and y in W, the space of homomorphisms from the projective functor theta x to the projective functor theta y is a free module over the coinvariant algebra, and the basis of this free module can be naturally identified with a basis in the space of all G homomorphisms from the indecomposable projective module Px to the indecomposable projective module Py. In particular, it follows that the monoidal category P00 is finitary in the sense that it has only finitely many indecomposables, and all home spaces in this category are finite dimensional. So the category O admits a graded lift, which can be constructed as a corollary from Zergil's combinatorial description of category O. So this says that the category O0 has a unique indecomposable projective injective module, namely the module PW0. Here W0 is the longest element in W. The endomorphism algebra of this module is isomorphic to the coinvariant algebra C, and this algebra is Z-graded in such a way that we put generators of this algebra in degree 2. The functor of taking G homomorphisms from this projective injective module into any module in the category O0, and this is a functor with domain O0 and the target category, the category of all finite dimensional C modules, this functor is full and faithful on projectives. Furthermore, the image of an indecomposable projective under this functor is a Z-graded module for any indecomposable projective module in the block O0. So consequence, the finite dimensional associative algebra underlying the category O0 is naturally Z-graded. So this algebra is defined as the opposite of the endomorphism algebra of the direct sum of all indecomposable projectives. And we know that this algebra is isomorphic to its opposite, so therefore there is no opposite here. So we can now define the graded lift of category O as the category of all finite dimensional Z-graded modules over the Z-graded algebra A. This graded lift is denoted by O0 with upper Z. All structural modules in O admit graded lifts. So we denote by LW the simple graded module, which is concentrated in degree 0. We denote by PW the graded cover of LW, so it has a top concentrated in degree 0. We denote by delta W the graded Verma cover of LW, again it has top concentrated in degree 0. We denote by IW the graded lift of IW, which has Sokal concentrated in degree 0. We denote by nabla W the graded lift of the dual Verma module, which has Sokal concentrated in degree 0. And finally, we denote by TW the graded lift of the tilting module such that the unique subquotient isomorphic to LW in TW lives in degree 0. Projective endofunctors of O0 also admit graded lifts. So the theorem due to Zörgel and Stroppel that each indecomposable projective functor has a graded lift which is unique up to isomorphism and shift of grading. Normalization, we will denote by theta W the indecomposable graded projective functor which maps the indecomposable graded module PE to the indecomposable graded module PW. And no graded shifts are involved in this equality or isomorphism. So we denote by P00Z the monoidal category of graded projective endofunctors of the graded version of category O. So for any simple reflection S, we have the corresponding indecomposable projective functor theta S, which is called translation through the S wall. And we know how theta S acts on Verma modules. So we know that there are short exact sequences. So if we have an element W in the while group such that WS is greater than W, then we have a short exact sequence. Delta W with graded shift -1 is a submodule of theta S delta W, and this has a quotient delta WS. The other case, when Ws is smaller than W, then delta Ws is a submodule of the module theta S applied to delta W, and the quotient is delta W with a graded shift 1. So we also know how theta S act on projective modules, so there are easier cases and more complicated cases. The easy case is that when we apply theta S to PW, in the case when WS is smaller than W, then we just get PW twice and shift it in the gradient by 1 and -1. And the easy values of theta S on simple modules, if we have W such that WS is greater than W, then such LW is killed by theta S. Combinatorics of category O can be described using the Hecke algebra. So the Hecke algebra H of W is the associative algebra over the algebra of all Laurent polynomials with integer coefficients in the variable v. So we denote this algebra by A. And the Hecke algebra is generated by the elements Hs, where S is a simple reflection, subject to the relation that Hs plus V times Hs minus V inverse is equal to 0, and also the usual braid relations. The Hecke algebra has a standard basis consisting of the following elements. If we have W in W with a fixed reduced decomposition, we denote by HW the product of the corresponding HS's following the reduced decomposition of W. Because the generators of the Hecke algebra satisfy the braid relations, the element HW does not depend on the choice of a reduced decomposition of W. The Hecke algebra has a bar involution, denoted by bar, which is a unique automorphism of H, which sends V to V inverse and HS to HS inverse for any simple reflection S. The algebra H has the so-called Kazhdan-Lusztig basis, which is defined by the following properties. For any W in W, there is a unique element in H, denoted by HW underlined, which is invariant under the bar involution, and which has the following form. When we write it as a linear combination of elements of the standard basis, HW underline is equal to HW plus a linear combination of standard basis elements with coefficients which are polynomials in V without constant term. And Kazhdan-Lusztig polynomials are defined as entries of the transformation matrix from the standard basis to the Kazhdan-Lusztig basis. We also have the symmetrizing trace form on the Hecke algebra, which maps an element written in the standard basis to the coefficient at the standard basis element He. And using this symmetrizing trace form, we can define the dual Kazhdan-Lusztig basis of the Hecke algebra as a unique basis HW underline hat, which has the property that the value of tau at the product Hx underline Hy inverse underline hat is equal to delta xy. So here delta is the Kronecker delta. And this should be true for all xy in W. So we have already seen that the action of projective functors on category O categorifies the regular Hecke module. So we start with the ungraded version of this statement. There's a theorem due to Bernstein and Guilfand. The Grothendieck group of O0 can be naturally identified with the free Z module with the basis given by elements of the Weil group, where the class of the Verma module delta W is sent to the element W. The Grothendieck ring of the projective functors P00 can be naturally identified with the integral group algebra of W by sending the class of the functor theta s to the element E plus S. And the action of P00 on O0 categorifies the right regular module over the integral group ring of W. This means that if you consider the action of P00 on O0 and take the Grothendieck group construction, we get the action of the integral group algebra ZW on itself, given the right regular representation of this algebra. So the graded version of this theorem can be attributed to Zergel and asserts that the Grothendieck group of the graded version of category O can be identified with the Hecke algebra under the same convention that the classes of the standard module delta W, now the graded standard module, is mapped to the element HW in the standard basis of H. So the graded Grothendieck ring of the monoidal category of graded projective endofunctors of O0 is also isomorphic to H, now as rings, by sending the class of the graded projective functor theta s to the element Hs underlined of the Kazhdan-Lusztig basis. And the action of this monoidal category of graded projective functors on O0 categorifies the right regular module over the Hecke algebra. So we have seen that there is a Kazhdan-Lusztig conjecture, which was proved by Beilinson, Bernstein, and Brzezinski-Kashevara, which implies that the isomorphism between the Grothendieck group of the graded version of category O and the Hecke algebra. So this isomorphism, as we saw, it sends the class of the graded standard module to the element of the standard basis. This isomorphism sends the class of the graded indecomposable projective module PW to the element HW underlined of the corresponding Kazhdan-Lusztig basis. As a corollary of this, directly from the classification of projective functors, it follows that the isomorphism between the Grothendieck ring of the monoidal category of graded projective endofunctors of O0 and H, which sends the class of theta S to the element HS underlined, it sends the class of theta W to the element HW underlined. So let us now discuss various bases and a bilinear form on these Grothendieck groups. So, as we already said, the standard isomorphism between the Grothendieck group of the graded version of O0 and H, it sends the classes of Verma modules to the element of the standard basis, the classes of the indecomposable projective modules to the elements of the Kazhdan-Lusztig basis, and it also sends the classes of the simple modules to the elements of the dual Kazhdan-Lusztig basis. We also have several additional bases in H, which follow directly from this categorification statement. We have a basis which is given by the classes of indecomposable injective modules. We have a basis which is given by the classes of the dual Verma modules. And we have a basis which is given by the classes of indecomposable tilting modules. Additionally, we can point out that on the Grothendieck group of category O, we have a natural bilinear form defined as follows. So the value of this bilinear form on the classes of two modules M and N is equal to the sum over all I greater than or equal to 0 minus 1 to the power I, and then we have the dimension of the i's extension from M to the dual of N. And it's a nice exercise to relate this bilinear form to the standard bilinear form on the Hecke algebra, which is defined using the symmetrizing trace form tau. Here's an SL2 example. For the algebra SL2, the Weil group is isomorphic to the symmetric group S2 and has two elements E and S. The graded picture of the structural modules in O0 is as follows. The module LS is a simple concentrated in degree 0. LE is a simple concentrated in degree 0. Delta S is equal to LS. Delta E has top in degree 0 and socle in degree 1. So PS has a Verma flag of length 2 with the Verma delta S in the top, and then the Verma delta E, which starts in degree 1, and PE is equal to delta E. Nabla S is the simple S, it's LS. Nabla E is a dual of delta E, so it's delta, and then we flip with respect to 0, so we get Nabla E. The indecomposable module IS, it is isomorphic to a shift of PS by 2, because S is a W0 at the moment, and the corresponding injective module is also projective. And IE is isomorphic to Nabla E. So the tilting module TS is simple and is concentrated in degree 0, and the tilting module TE, it's isomorphic to PS and to IS up to shift, and it is shifted so that the summand LE is concentrated in degree 0. And the corresponding elements in the Hecke algebra look as follows. So the class of LS is HS, because it's a standard module. The class of LE is HE minus VHS. So we take delta E and we should subtract LS, which is HS, but shifted to the degree 1. So the class of delta S is HS, the class of delta E is HE, so this is a standard convention. The class of PS is HS plus VHE, so this is a delta filtration of PS. So the class of PE is HE. The class of Nabla S is HS because it's simple and standard. The class of nabla E is equal to V inverse HS plus HE minus V HS. So this is the most non-trivial part. We should take the projective module PS, shift it, and then subtract LS, also shifted. So we get this expression. So the class of IS is V to the power minus 2 HS plus V to the power minus 1 HE. This is PS shifted 2 steps up. The class of IE is the same as the class of nabla E. The class of TS is just HS, and the class of TE is the class of PS shifted by one step up. So let's go to the second categorification result. And first we discuss the Hecke analog of the induced sign module. Let P be a parabolic subalgebra of G, and WP the corresponding parabolic subgroup of W. So let SP be the set of simple reflections which generate WP. And HP denote the Hecke algebra of WP, which we consider as a subalgebra of H. So recall that for any simple reflection S, the element HS satisfies the equation HS plus V times HS minus V inverse is equal to 0. So in particular, the possible eigenvalues for HS are minus V and V inverse. This allows us to consider the HP module, which as an abelian group is equal to our ring A, and here indices P means that this will be a module for HP, and minus V means that for any simple reflection S in SP, the action of HS on the element 1 in this module is given by minus V. So we prescribe that HS has on this module the eigenvector with eigenvalue minus V. So this is one of the two possible eigenvalues. Then the parabolic Hecke module NP is defined as the module which is induced from this module AP minus V over HP all the way to H. Let us denote by V modulo WP on the left, and then short, the set of all shortest coset representatives in these cosets. Then directly from the definition, the module NP has a natural basis given by the elements NW, and this is a notation for the element A, for the element 1 tensor HW, where W is an element in the set of shortest coset representatives. And it is very easy to check that the action of the Kazhdan-Lusztig element HS underlined, where S is now any simple reflection, on the element NW is given by the following formula. So if WS is a shortest coset representative and is greater than W, then the outcome is NWS plus VNW. If WS is the shortest coset representative and is smaller than W, then the outcome is NWS plus V inverse NW. And in all other cases, the outcome is 0. So next we need to look how translations through walls act on parabolic Verma modules. Let S be any simple reflection and W a shortest coset representative. Then, in the case when WS is a shortest coset representative and is greater than W, then if we consider the module theta S applied to the parabolic Verma module delta WP, this has the quotient delta WSP, and the kernel is isomorphic to delta WP shifted by -1. In case WS is the shortest coset representative which is smaller than W, then delta WSP is a submodule of theta S delta WP, and the quotient is isomorphic to delta WP shifted by 1. And in the case when WS is not the shortest coset representative, then theta S applied to delta WP is equal to 0. Proof. Let Zp from O to the parabolic category be the Zuckerman functor defined as taking the maximal quotient in the parabolic category. So in order to prove the first two statements, we apply the Zuckerman functor to the short exact sequences associated with translations of the usual Verma modules. So we know that theta s delta w has a Verma flag of length 2, and in the case when ws is greater than w, we have the quotient delta ws and the submodule delta w shifted by -1. In the case when ws is less than w, we have delta ws as a submodule and delta w shifted by 1 as a quotient. So we can apply the functor zp to these short exact sequences, and since the functor zp is only right exact, we will get two right exact sequences. But we know that both the module theta s delta w, it has a standard filtration in category O, and the corresponding module theta s delta wp has a standard filtration in the parabolic category. From this it follows that the outcome of the application of ZP to these short exact sequences must be short exact sequences. And this proves the first two statements. And the last claim follows from the following observation. If Ws is not a shortest coset representative, then it is easy to see that Ws is greater than W, and then the module theta s delta W has simple top LWS, which doesn't survive the application of Zp. Therefore, if we apply Zp to this translated Verma module, we will get 0. So this proves this proposition. So now we can use it to show how we categorify the Hecke module NP using the parabolic category O. We have an isomorphism psi p of abelian groups between the graded version of the trivial block of the parabolic category OP and the Hecke module NP, which sends the class of the parabolic Verma module delta WP to the element NW, where W is the shortest coset representative. Clearly, the action of projective functors on category O preserves the parabolic subcategory. So therefore, the action of graded projective functors on the graded version of the trivial block in the parabolic category categorifies the Hecke module NP. In the same sense as we used before, if we apply the Grothendieck group construction to this monoidal category acting on this abelian category, we get exactly H acting on the module NP. And to prove this, we just compare the short exact sequences for the actions of the translations through walls on the parabolic Verma modules with the formula which describe the action of the Kazhdan-Lusztig element Hs underlined on the standard basis NW of the parabolic Hecke module NP. We compare this proposition with these formulas, and we see that they precisely match. And this implies this categorification result. And since the elements Hs underlined generate the Hecke algebra, the claim follows. So if we forget the grading, we just get that the action of the monoidal category of projective functors on the trivial block of the parabolic category OP categorifies the induced sign module. So we take the sign module over the parabolic subgroup WP and deduce it up to W. If we evaluate V at 1, then we see that this parabolic Hecke module NP becomes the induced sign module, because the module AP minus 1 is exactly the sign module over the integral group algebra of WP. So the parabolic Hecke module NP has an analog of the Kazhdan-Lusztig basis. Lemma, there is a unique endomorphism of NP, which is denoted by bar, which has the property that NE bar is equal to NE, and NH bar is equal to N bar H bar for any element N in our module and for any element H in H. This is very easy to see. Here is the theorem, which is due to Deodar from 1987. For any shortest coset representative W, there is a unique element NW underlined, which is self-dual with respect to the bar involution and which has the form NW underline is equal to NW plus a linear combination of other standard basis elements with coefficients which are polynomials in V without constant term. And this basis one can call either a Kazhdan-Lusztig basis or the canonical basis of this parabolic Hecke module. A consequence of this is that our isomorphism psi p between the Grothendieck group of the graded version of the trivial block of the parabolic category O, which sends the classes of parabolic Verma modules to the elements of the standard basis, it maps the classes of the indecomposable projective modules to the elements of this Kazhdan-Lusztig basis. And here, of course, the point is that applying the indecomposable projective functors to the dominant standard modules, we get exactly the indecomposable projective modules in the principal block of the parabolic category O. There are several other bases in the Grothendieck group of the graded version of the trivial block of the parabolic category, which is given by the classes of simple modules, by the classes of costandard modules, by the classes of injective modules, and by the classes of tilting modules. So the Grothendieck group inherits from the parabolic category O several bases. So here is an SL3 SL2 example. So if we consider the Lie algebra SL3, the Weil group is the symmetric group S3 and has the elements E, S, T, ST, TS, and W0, which is STS or TST. Let's take the parabolic subgroup given by the elements E and S. Then the set of shortest coset representatives consists of the elements E, T, and TS. So here are the standard and projective modules in the parabolic category. So the standard module corresponding to TS is simple, concentrated in degree 0. The standard module corresponding to T has T in the top, concentrated in degree 0, and TS in the socle. And the standard module corresponding to the element E has E in the top, degree 0, and T in the socle, degree 1. The indecomposable projective modules look as follows. The indecomposable projective cover of LE is just the standard module. The indecomposable projective cover of LT has Verma flag with delta T on top and then delta E in the bottom, also shifted by 1. The indecomposable projective cover of TS has delta TS on top and delta T in the bottom, also shifted by 1. And finally, we have the following indecomposable tilting modules. The tilting module for TS is simple, concentrated in degree 0. The tilting module for T is actually the projective injective module for TS, but it is shifted so that the subquotient T lives in degree 0. And finally, the indecomposable tilting module for E is also projective injective. It's a projective cover for PT, and it is shifted so that the subquotient LE lives in degree 0. And this example can be generalized, actually. In the general case, if you consider the regular block of category O for SLN with a parabolic given by SLN minus 1, then the Weil group is a symmetric group Sn generated by simple reflections S1, S2, and so on, Sn minus 1. And we assume that the parabolic subgroup is generated by simple reflections S2, S3, and so on, Sn minus 1. Then the set of shortest coset representatives consists of the elements E, S1, S1, S2, S1, S2, S3, and so on. We denote these elements by V1, V2, V3, Vn. And then one can compute that the quiver of the regular block of the parabolic category O, in this case, looks as follows. So the vertices of this quiver are, of course, the elements of our set of short coset representatives. And then we have the arrows. So one arrow from V2 to V1, one arrow from V3 to V2, and so on. And then one arrow in the opposite direction. And the relations are as follows. going two steps in the same direction is 0. So going two steps to the right or to the left is 0. So if we start from any vertex and go one step to the right and then to the left, we'll get the same as going one step to the left and then coming back to the right. And the final relation is that the loop at the vertex v1, so beta 2 and then alpha 2 is equal to 0. So this is the description of this parabolic category by quiver and relations. And the Kazhdan-Lusztig basis here, in this case, for the parabolic Hecke module, looks as follows. Of course, the dominant element is just the standard basis element, and then the indecomposable projective in V2 has standard filtration of length 2 with its standard module starting in degree 0, and then the standard module HE starting in degree 1. The indecomposable projective in V3 has its standard in degree 0 and the standard corresponding to V2 in degree 1, and so on. So all indecomposable projectives apart from the first one has Verma flag of length 2. Okay, so let us consider the third categorification result, and this is a Hecke analog of the permutation module. Again, recall that for any simple reflection S, the only two possible eigenvalues for the element Hs are minus V and V inverse. So we have already considered the case of minus V. Now we are talking the case of V inverse. So we consider our Laurent polynomial ring as a module over Hp, where the action of Hs is given by multiplication with V inverse. And we define the parabolic Hecke module MP as the module which is obtained from this module over Hp by tensor induction all the way up to H. And then, of course, the natural basis of MP is given by elements MW. This is a notation for one tensor HW, where W is the shortest coset representative. And the action of the element Hs underlined on the element MW is given by the following formulas. If Ws is the shortest coset representative and is greater than W, then we get MWs plus VMW. If Ws is the shortest coset representative and Ws is smaller than W, then we get MWs plus V inverse MW. And finally, if Ws is not the shortest coset representative, we get V plus V inverse MW. Recall that in the last lecture we looked at S-subcategories in O. So we considered the category SP0, the S-subcategory in O, which corresponds to the element P. We also considered the set of longest coset representatives in W with WP acting on the left. So recall that on the one hand we can describe S0P as a quotient of O0 by the third subcategory generated by LW, where W is not the longest coset representative. And the second point of view was that S0P is a full subcategory of O0, which consists of all modules having a two-step presentations by projective modules in which each indecomposable summand is isomorphic to PW, where W is the longest coset representatives. So we have seen that this category is a category of modules over a properly stratified algebra, where the standard modules are delta Ws, W is the longest coset representative, and this module is defined as a quotient of PW, modulo the trace in PW of all projectives which correspond to longest coset representatives, which are smaller than W in the Brugha order. Alternative description is that delta Ws is a module which is parabolically induced from the projective injective module in the category O for the Levy quotient of P. And we have the property that the module delta Ws has a Verma flag in category O, and in this Verma flag, each Verma subquotient delta X, where X is an element from the WP coset of W, so each such Verma module appears once. So next we have to look what happens if we apply translations through walls to these standard objects in the S subcategory in O. So the claim is that for any simple reflection S and for any longest coset representative W, we have the following cases. If WS is greater than W and is a longest coset representative, then theta S delta WS surjects onto delta WSS, and the kernel is delta WS shifted by -1. If WS is greater than W and is a longest coset representative, then theta S delta WS surjects onto delta WS shifted by 1, and the kernel is delta WSS. In the remaining case, when WS is not the longest coset representative, then theta S delta WS is delta WS shifted by 1 plus delta WS shifted by -1. To prove this, let's denote by X the longer element in the set W and WS, and by Y the shorter element in this set. The module theta S delta WS has a standard filtration. This is the usual thing for parabolic induction. By junction, we know that the module theta S delta WS surjects onto delta XS in the ungraded version. So here we use that X is a longer element out of W and WS. We also have by junction that delta YS injects into theta S delta WS. Now checking the gradient of Verma subquotients in category O, we obtain the first two claims of this proposition. And the last claim follows easily from the observation that under the assumptions of the last claim, theta S applied to the indecomposable projective PW simply doubles it and shifts by 1 and -1 in the gradient. This implies the last formula. As a consequence from this, we have the following categorification of the permutation module using S subcategories. We have an isomorphism phi-p of abelian groups between the Hecke module MP and the Grothendieck group of the category of perfect complexes for the graded version of the trivial block of the S subcategory SP, which sends the class of the standard module delta WS to the standard basis element M with the index W0PW. So here we need this change because for the standard module, W is the longest coset representative, and for the indexing set of the standard basis is in MP, we need shortest coset representatives. So what we need is just to multiply the longest coset representatives with the longest element in our parabolic subgroup. We have already discussed that the action of projective functors on category O preserves the S subcategory. So in particular, it preserves projective objects in the S subcategory, and hence the category of perfect complexes for the S subcategory. The claim is that the action of the graded version of projective functors on the category of perfect complexes for the graded version of the SER subcategory categorifies the parabolic Hecke module MP. In other words, this means that applying the Grothendieck group construction to the graded version of projective functors, acting on this category of perfect complexes over the S subcategory, we get the action of the Hecke algebra H on the module MP. And to prove this, we just need to compare the formulas for the action of simple reflections on standard modules with the formulas for the action of the elements HS underlined on the standard basic of the Hecke module. So we see that these formulas correspond. And in the ungraded version, we get the corollary that the action of projective functors on the category of perfect complexes for the ungraded version of the trivial block of the S subcategory in O categorifies the permutation module, which is the module induced from the trivial module over the parabolic subgroup W. P. And for this, we just forget the gradient, that is, we evaluate V at 1. Similarly to the previous cases, we have various bases in our module. So we have the basis given by standard modules, and we have the basis which is given by indecomposable projective modules. So this is the Kazhdan-Lusztig basis, and this is the most natural basis for the category of perfect complexes. So standard modules give a basis because each indecomposable projective has a standard flag. Then we have the basis given by indecomposable tilting modules, again due to the fact that each indecomposable tilting module has a standard flag with some triangular properties. Next, we use the fact that each tilting module is cotilting, and all cotilting modules have a filtration by costandard modules to get that we have a basis given by the classes of costandard modules. And finally, since each indecomposable injective module has a costandard flag, we also have a basis given by the classes of indecomposable injective modules. So here it is very important that tilting modules in S subcategories are also cotilting. So this observation in particular implies that both costandard and injective modules in S subcategories in O have finite projective dimension. There are three classes of modules which are not mentioned here: simples, proper standard modules, and proper costandard modules. In the general case, these do not have finite projective dimension, and hence they do not belong to the category of perfect complexes. So here is an SL3, SL2 example. So if we have SL3, where W consists of E, S, T, ST, TS, and W0. So we take WP equal to E and S, and then the set of longest coset representatives is the set S, ST, and W0. Then we can consider the standard modules in the S subcategory SP as objects in category O, and then they have the corresponding graded Verma filtrations. So delta SS has delta S as a quotient and delta E shifted by -1 as a submodule. Delta ST in the S subcategory has delta S as the quotient and delta T shifted by -1 as a submodule. And delta W0S in the S subcategory has delta W0 as a quotient and delta TS shifted by -1 as a submodule. So applying theta S, we get that theta S, delta S in the S subcategory, has delta S in the S subcategory shifted by 1 as a quotient, and delta S in S subcategory shifted by -1 as a submodule. So in this case, we have a splitting into a direct sum. And this is because S times S is no longer a longest coset representative. So theta S applied to delta ST in S subcategory has as a quotient delta W0S and as a submodule delta STS shifted by -1. And theta S delta W0S, this is isomorphic to theta S delta STS up to shift. It has delta STS as a submodule and delta WS shifted by 1 as a quotient. On the other hand, applying theta T, we get that theta T applied to delta SS has delta STS as a quotient because S times T is again longest coset representative, and delta SS shifted by -1 as a submodule. And the same module is up to shift isomorphic to theta T delta STS, and it has delta SS as a submodule and delta STS shifted by 1 as a quotient. So theta T applied to delta W0S is a direct sum of delta W0S shifted by 1 and by -1. This is because T times W0 is no longer the longest coset representative. Here are some questions for PhD students. Question number 1. Explore the connection between the bilinear form on the Hecke algebra given by tau and the bilinear form on the Grothendieck group given by the alternating sum of the dimensions of the ICE extension groups. Question number 2. Compute explicitly in the standard basis The images in the graded Grothendieck group of the indecomposable injective modules in category O for SL3. Question number 3. Prove that for any simple reflection S and any shortest Cauchy representative W, the property Ws less than W implies that Ws is a shortest Cauchy representative. Question number 4. Prove with all details that the quiver and relation description of the principal block of category O for the parabolic version of SLN with parabolicity SLN-1 is the correct one. And question number 5, provide all the details for the proof of the claim describing the action of theta S on standard objects in the S subcategory of O. Thank you very much and see you next time.